Okay, so it's our pleasure to have here today Jorge Delgado,
Mhm.
that is performing his PhD doctorate studies at the University of Aveiro under the supervision of Professor Carlos Herdeiro. So, Jorge, the stage is yours. Thank you.
Thank you. So, firstly, I'd like to thank Professor Crispino for the invitation to give this seminar. So, as he said, I'm Jorge Delgado, and I'm here to talk about the recent work that we did in collaboration with Professor Carlos Herdeiro and Dr. Eugene Radu about time-like circular orbits and the efficiency of compact objects. This is a recent work that is published in arXiv if you want to read it, and we submitted to JCAP. So, in 2017, in this paper, the authors shown that for a very generic horizontless object, that object, if it is ultra-compact, can have a pair of light rings, in which the outer one is always unstable and the inner one is always stable. In a similar manner, the same authors some years later showed that in the case of a black hole, the black hole always has at least one light ring which is unstable. These two papers are very interesting. They show very interesting results, but they only analyze null geodesics, aka the light rings. But here I'm a bit more interested in the ask and study what happens to the time-like geodesics. Does this structure of for the null geodesics imply some structure for the time-like case? And in fact, as I will show you, in the fact they will. So what I'll show you is that for the ultra-compact horizontless object, the region between the two light rings will be always a region with no time-like circular orbits. And for the black hole case, the region between the horizon and the light ring will be a region of also no time-like circular orbits as well. So in order to show this, we start by considering a very generic spacetime. So here I consider a stationary asymmetric asymptotically flat in 4 dimensions spacetime, which due to the symmetries, mainly stationary and the axisymmetry, together with some gauge choice, we can write this very generic metric, which basically represents an object which is rotating, which may or may not have an horizon, and well, essentially is just that. We also impose a north-south Z2 symmetry, which is essentially says that there is a north and a south pole, hemisphere, which are equal. Then, due to this, the equatorial plane is a total geodesic submanifold, and it's on this plane that we'll study geodesics, or in other words, circular orbits. So, in order to have a circular orbit, we'll consider the effective Lagrangian of a test particle, which is given here. So this xi might be -1 for time-like particles, 0 for null particles, or 1 for space-like particles. With that, using the symmetries of the problem, we have two killing vectors, which can be related with the energy and the angular momentum of the test particle. And with that, we can put in this equation, we obtain this expression, where a and b are two functions given by these two equations, where I note that this b function is always positive, and which will be interesting later on. Then, in order to have circular orbits, we have to define effective potential, which is basically just the GRR component of the metric times r dot squared. So it's essentially this equation. And to have circular orbits, we have just to say that this potential must be equal to 0, as well as its first derivative. This gives these two equations, simple equations, that one has to solve. After solving both equations, we can look into the stability of that orbit, and that's done by checking the sign of the second derivative of the potential. If it is positive, then we have an unstable circular orbit, but if it is negative, then we have a stable circular orbit. For a very generic stationary spacetime, when we solve these two equations, usually we get two different pair of solutions. One is associated to co-rotating orbits, which we denoted with a plus sign, and the other is associated with counter-rotating orbits, which we associated with a minus sign. So let's start by looking to null geodesics in which the xi is equal to 0. In that case, the circular orbits are light rings. So we look into the potential for the null particles, so xi is 0. We get these two equations. The first one gives an expression for this sigma, which is known as the inverse impact per meter. So the energy divided by the angular momentum of the test particle. And the second one gives the radial coordinate of the light ring. With that solved, we can look into the stability of the light ring and we get this expression. So this term here, L square, is always positive since it's a square. This term here in the denominator is the b function, and as I said, is always positive. So the sign of the second derivative only depends on the numerator. So if the numerator is positive, we have an unstable light ring. If it is negative, we have a stable light ring. Now, if you study the timelike orbits, now c is -1. Now it's a bit more trickier, but we can simplify the results by introducing the angular velocity of the time particle measured at infinity. With that, we look into the first equation, the potential equal to 0, but now for time-like particles, so -1, and we obtain these two expressions for the energy and the angular momentum of the particle, time-like particle. So we also have here this beta function that I highlighted in red and is given by this expression, and I highlighted because in the few slides it will be important. Then the second equation, which is the derivative of the potential equal to 0, gives this simple expression, and with that we can obtain an analytical expression for the angular velocity written only in terms of the metric components, where this c is also highlighted in purple and is given by this expression because, again, will be important a bit into slides. So we then can look into the stability, and we have this a bit more complex expression, but it's not very interesting. But usually what we have is something like this diagram. For example, this happens for Kerr, for Schwarzschild, for Kerr-Newman, and other types of black holes, in which we have a region connected to infinity, which has stable time-like circular orbits, in which the second derivative is negative. Then, closer to the object, we have a region where we have unstable time-like circular orbits, in which the second derivative is positive. And in the threshold of these two regions, we have a circular orbit in which the second derivative is equal to 0. And this is called the ISCO, or the innermost stable circular orbit. But this is what happens, for example, for Kerr. But for a very generic ultra-compact object, there may be several solutions for when you compute that the second derivative of the potential is equal to 0. So we could have several ISCOs. So in order to be a bit more easy to understand everything, we defined what we call the standard ISCO, which is the solution with the largest radial coordinate such that the second derivative is equal to 0, and the third one is negative. This is here just to ensure that outside of the ISCO you have the second derivative negative, so a region of stability, and within the ISCO we have a region of instability where the second derivative is positive. But if you were looking closely, when I introduced the angular velocity, I introduced that c function, which was within a square root. So if for some reason this c function is negative, for some reason, then there cannot be any circular geodesics, neither space-like, neither null, neither time-like. So we could have something like this, where we have an object where there's some region where this c function is negative, so you don't have any circular orbits at all, and then it's connected to a region where c is positive, and that region corresponds to a region where we have stable time-like circular orbits, something like this. So by the definition of ISCO, so it's the innermost stable circular orbit, this should be an ISCO as well. So in this case, we defined the absolute ISCO, which is either the solution with the smallest radial coordinate such that the c function is equal to 0, and if you consider a point or circular orbit slightly above the absolute icicle, in which the second derivative of the potential is negative, then we have this absolute icicle, because this part here is just to ensure that we have a stable region outside of the icicle. Then the absolute icicle can be this, or we can consider the solution with the smallest radial coordinate, such that again the second derivative of the potential is 0 and the third one is negative. So here, instead of considering the largest solution, so the solution with the largest radial coordinate, such as in here, instead of considering the largest one, we consider the one that is closest to the center object. Now, with everything defined, we can look into one of the main results of our work, which is that the stability of a light ring determines the possibility and stability of time-like circular orbits around it. And in order to show this, we then will look into that beta function that I mentioned before. And we can see that, or I will show you, that when beta is equal to 0, we have a light ring. And this can be seen by first writing the B function and equal it to 0. And by solving this equation, we see that the angular velocity of the time-like particle is equal to the inverse impact parameter. Then, in order to show exactly that beta equals to 0 corresponds to a light ring, we have to solve, or we have to obtain that the first derivative of the potential for null particles at that circular orbit is indeed equal to 0. So to do that, we write the derivative, so it's here. Then, using this first result and using the definition of the angular velocity for a circular orbit that we obtained by solving this equation before, we can show that, in fact, this will always happen. This means that, in fact, when beta is equal to 0, we are on a light ring. So this is a quite interesting result, but why is that so important? It's important because when we study the energy and angular momentum of time-like particles, we saw that it goes as 1 over the square root of beta. So we can see that on the light ring, the energy and angular momentum go to infinity. They are not defined, or well defined. But most interestingly, there is a square root here, meaning that if we consider a region close to the light ring, if beta is negative, then the energy and angular momentum are complex. Therefore, you cannot have any time-like circular orbits. But if beta is positive, then the energy and angular momentum are real. Therefore, you can have time-like circular orbits, although you don't know if they are stable or unstable. So, in order to see if this beta goes to negative or positive values, we can do a Taylor expansion of beta around the light rings. So in first order, we get only the first derivative of beta function times a displacement, a radial displacement compared to the light ring. So if you are above the light ring or below the light ring. And by solving that, we obtain this expression, which, very briefly, this is a positive quantity, is a square root. This is this is a power of 2. Then we have here is the square root of this quantity, which what comes out of a square root is always a positive number. Then the sign of beta depends only on the stability of the light ring and the displacement. So if you are above the light ring or below the light ring. So in order to see this a bit easily, consider that now you have an unstable light ring. So this quantity is positive. In that case, what we have is that below the light ring, we have a region where beta is negative. Therefore, you don't have any time-like circular orbits here. But if you consider the region above the light ring, then you have a region where beta is positive. Therefore, you can have time-like circular orbits, although you don't know yet their stability. In a similar way, if you consider now a stable light ring, basically what we have is the reverse. The inner region is the region where we have time-like circular orbits, and the outer region is a region where you don't have any time-like circular orbits. But you can go a bit further by trying to look into the stability of these regions where you have time-like circular orbits. And in order to do that, we have to study the second derivative of the potential for time-like circular orbits, which can be written in this way. If you look a bit closely, you see that there's the beta. So if you compute this at the light ring, beta goes to 0, so this first term diverges. And since the second one is always finite, close to the light ring, this term will always be will not enter to the computation because this term is always way larger than this one. So we only have to look to this first fraction. So since we want to approach the light ring through the region where beta is positive, because we are approaching the light ring through this region where we have time-like circular orbits, beta is positive, and here, then we approach the light ring through values of positive beta. Then this part here is the B function, which again is always positive, so the denominator is always a positive number. So in order to see if the stability diverges towards plus infinity or minus infinity, you only have to look into the sign of the numerator. And if you compute the numerator at the light ring, we get this very simplified result in which this fraction is always positive, since we have the squares. So the sign of this numerator will only be dictated by the stability of the light ring. In the end, what we have to complete the diagram is something like this. For the unstable light ring, the region above it will always be a region of unstable time-like circular orbits, since the stability will be positive. So the second derivative of the potential is positive. And for the stable case, the inner region of the stable light ring will always be a region of stable time-like circular orbits, since the stability is now negative, or the second derivative is now negative. This is one of the main results of our work. And with this result, we can show that in the case of ultracompact horizontless objects, the region between the two light rings will always corresponds to a region where we don't have any time-like circular orbits, because in this region beta is negative. And if you want to consider a different region here, for example, of stable time-like circular orbits or unstable ones, then in some region between the light rings, there must be a region where beta is positive. And by continuity, from going from negative values of beta to positive values of beta, we have to cross beta equal to 0. And that, as we saw, will always imply the existence of another light ring. But here, we are only considering the existence of these two light rings. Therefore, this region must always be a region where beta is negative, and therefore a region without any time-like circular orbits. In a similar fashion, you can show the same way that in the case of a black hole, the region between the horizon and the unstable light ring will always be a region without any time-like circular orbits. We can also see that above above the unstable light ring, we have unstable time-like circular orbits, and within the stable one, we have stable time-like circular orbits. Now, I will show you this exact structure for some examples, some stars and some black holes, because now in my second part of the presentation, I will talk about the efficiency. And this efficiency, very briefly, is just an estimate for the amount of gravitational energy which is converting to radiation as the time particle falls from the infinity until we reach the ISCO, and is very briefly computed by this expression. Now, as you may remember, we defined two types of ISCOs. We have the standard ISCO and the absolute ISCO. So we also will have to define the standard efficiency and the absolute efficiency. In the case of the standard efficiency, we consider the time-like particle, which is falling through a series of standard time-like circular orbits until it reaches the standard ISCO, and there you define the standard efficiency. In a similar way, you can define the absolute efficiency as some particle which is falling through a series of time-like circular orbits until it reaches the absolute ISCO, and there you compute the absolute efficiency. So Now I will compute this quantity and I will show the results for two classes of stars and two families of black holes. For the stars, I will talk about spinning scalar boson stars and I will show the results for two specific families of this class. Here we have the ansatz for the scalar field. And I will talk about one family of spinning vector boson stars. And again, we have here the ansatz for the vector field. So regarding the spinning scalar boson stars, I'll consider first the mini boson star case, where the azimuth harmonic index is equal to 1, and they are the solution of this action. Sorry. So let's first look into the structure of circular orbits for the co-rotating case. So here what I have, or what I show you, is the maximal value of the scalar field as a function of the radial coordinate. We do this because this way each horizontal line corresponds exactly to one solution. And with that, we can, for example, define this, choose this solution. And with that, you can see exactly how the structure of the circular orbits are. So if you are far enough, you are on the region of stable circular orbits, so the green region. But as you go closer, closer, closer into the star, we reach the absolute ISCO, in this case, which then within the absolute ISCO, we have a region without any circular orbits. But for example, if you consider a more compact solution, there is some small region, some disconnected regions of unstable timelike circular orbits. So in that case, what we have is something like this, where if you are far away, you are on the stable timelike circular orbits region. Then you reach the standard ISCO, where the unstable region starts. Then again, you can cross to a region of stability, and then reaches the absolute ISCO, and again, very close to the center of the star, we have a region without any circular orbits. So if you compute the efficiency, so here we have, again, the maximal value of the scalar field as a function of the efficiency. Again, this way each horizontal line corresponds exactly to one solution. We see that the absolute efficiency grows from 0 to very close to unity and grows very almost linearly. But for the compact solutions in which there is this small region of unstable timelike circular orbits, we also have defined here the standard ISCO. Therefore, we have also the standard efficiency. But since the standard ISCO appears a bit further away from the center of the star, the efficiency will always be small compared to the absolute one. So here in this case, it starts around to 25% and increases to 30 something percent. Now let's look to the counter-rotating case, which, as you can see, has a more rich structure. So here, for example, you can see that compact solutions starts to develop a pair of light rings. And for example, if I choose this solution in particular, you can see that there's several regions. So far away, again, you are on the stable region. Then we reach the standard ISCO, where the unstable region starts. Then we reach the pair of light rings, which the outer one is unstable and the inner one is stable. So here you can see that the region between both light rings is a region without any timelike circular orbits, as I mentioned in our result before. Here you can see exactly that. And you also can see that above the unstable one, we have unstable region, and below the stable light ring, we have a stable region. If you go closer to the center of the star, again, we reach the absolute ISCO and the region without any circular orbits. If we now look into the efficiency, the absolute efficiency is exactly the same as for the co-rotating case, so it grows almost linearly from 0 to 1. But the standard efficiency first appears much sooner because less compact object stars, in the mini boson stars in this case, appears this disconnect region of instability. So the standard ISCO appears much sooner and appear much further away from the star. So that's why the standard efficiency is quite small, as you can see. Now, moving for a different type or different family of boson stars, the axion boson stars. They are the solutions to this action, where this potential is given here. This is based on the QCD action potential, where this P is just a constant, mu A is the mass of the action particle, and Fa is the decay constant. And if you consider larger values of this decay constant, this potential basically converges into the mass potential. So if you consider large values of the decay constant, you have basically the mini boson star case. So we have the previous result that I showed. But if you consider small values, for example, 0.05 in this case, then the self-interaction part of this potential starts to grow. It starts to be bigger than the mass one. Therefore, we have different results. So if you look to the structure of cyclic orbits for the co-rotating case, we see that it's similar as for the mini boson star case, but this region of instability appears sooner and a bit further away. So the efficiency will also have some differences. So the absolute efficiency, again, goes from 0 to 1 very monotonically, but there is some curves, is not as linear as before. And the standard efficiency, again, happens sooner. And since the standard ISQ is a bit further from the center of the star, the efficiency is always smaller. In this case, starts around 15%, it's between 10 and 15, and increases to more or less 25. For the counter-rotating orbits, we see, again, a similar picture with some nuance. So the absolute efficiency grows again exactly the same as for the co-rotating orbits. It grows from 0 to 1 monotonically with some curves. And the standard efficiency now appears sooner. And since the standard ISQ is a bit further away from the star, the standard efficiency is also smaller compared to the previous case, this one. So let's move on and consider now a different kind of star, the vector Broca stars, which are the solution of this action. And in this case, the structure is much, much simpler because now for co-rotating orbits, we have stable timelike cyclic orbits all the way down until the center of the star, in which we defined it the absolute ISQ, if you want to consider it as an ISQ, since it's only a point at the center of the star. In that case, the efficiency grows again from 0 to almost close to 1, and it grows monotonically. For the counter-rotating orbits, it's a bit trickier, but for most solutions is exactly the same as for the co-rotating case. But for more compact solutions, they first start to develop a disconnected region of unstable time-like cyclic orbits, but then they can have two disconnected regions of unstable time-like cyclic orbits. And if you consider even more compact ones, they can also start to develop light rings. So for example, if I consider this solution in particular, the structure is something like this. You start far away on the region of stability, you reach the standard ISQ, and then we have a series of alternating stability regions. So unstable, stable, unstable, stable. And at the center, we have the absolute ISQ. So in terms of the efficiency, the absolute efficiency is exactly the same as for the co-rotating case. But then for the compact solutions, which have this first unstable region, you have the standard efficiency, which starts around 20% and increases a bit. But then as soon as the star starts to develop the second region of instability, the standard ISQ jumps to values, to radial values way larger. So the efficiency also drops quite a lot, as you can see. Now, I'll talk about stars. Now I will talk about two families of black holes. The first family is the Kerr black holes with synchronized axionic air, which is basically the natural black hole generalization of axionic boson stars. So here we can see the domain of existence where they all live. So here we are considering the same decay constant as for the axionic boson stars. So Fa is equal to 0.05. So here we can see in the red line the boson star line, and this blue region is where all the black hole solutions reside. Then the second family of black hole solutions are the Einstein scalar Gauss-Bonnet black holes, in which here we have the action. So this phi is a scalar field, which now it's real, and it's non-minimally coupled with the Gauss-Bonnet invariant. And here we have the domain of existence, where all solutions fall. Each orange square in this plot corresponds exactly to one numerical solution that we obtain. So as you can see, we obtain a lot. And in the thresholds of this domain, we have the curved black holes in the red line, the static black holes without any spin. We have the streamable set, which corresponds to solutions with a vanishing Hawking temperature. And then we have the critical set, which is the last line of solutions before they start to be or don't have any event horizon. So they are Nickel singularities. So let's study now the first solution, or the first family, Kerr black holes with synchronized axionic air with a decay constant of 0.05. And here we have the case for co-rotating orbits. So this now is a different plot. So now in the vertical axis, we have the efficiency as a function of the decay of the dimensional spin. Sorry. So this dash blue line is the Kerr line. So it starts at around 5% for Schwarzschild and increases until 42% for extremal Kerr. Then we have the red solid line corresponding to boson stars, the axionic boson stars. So here, this first line here is the absolute efficiency, and then this one is the standard efficiency. Then we have these two regions of blue, so this light blue and dark blue. For the light blue, what we have are hairy solutions that have a very Kerr-like structure, in the sense there is an horizon, there is one unstable light ring, and there is one ice core. And for that types of hairy black holes, we see that the efficiency can grow very close to unity, and obviously they can be very large, have much more efficiency than the value for the maximal for extremal Kerr. Then the dark blue region corresponds to hairy solutions that don't have a Kerr-like structure. So they may have an extra pair of light rings or different more regions of unstable time-like circular orbits. So they are what we call non-Kerr solutions. And even in that case, the efficiency does not grow as much as for the Kerr-like structure solutions, but they can have efficiencies larger than the extremal Kerr case, as you can see. For the counter-rotating case, here again we have the Kerr line that starts around 5% and decreases. And now the Kerr-like solutions that has a structure more or less like Kerr have a smaller efficiencies when compared to the co-rotating case, but anyways, they can have efficiencies larger than the ones for Kerr. Even the solutions that are no Kerr-like also have efficiencies that are bigger than for Kerr. Moving on for the final family of black holes. This case is much easier to analyze because all solutions have a Kerr-like structure. So here we have again the efficiency as a function of the dimensional spin. And in this case, the red solid line is the Kerr line. Are not spinning fast enough. The hairy solutions always have more efficiency than the Kerr ones with the same dimensional spin. But if you consider fast spinning solutions, the reverse happens. So now the Kerr solutions have more efficiency than the hairy ones for the same dimensional spin. For the counter-rotating orbits, we see that for solutions with the same dimensional spin, the hairy solutions are always the ones that have more efficiency, but the difference starts to decrease as we increase the dimensional spin. Although even in the maximal value, the difference is not very, very large. So let's now finalize everything that I said. and so that you can take some message home. So in the first part of my presentation, I showed that for a very generic stationary asymmetric and asymptotically flat compact object with a Z2 symmetry and in 4 dimensions, that if it has an unstable light ring, we expect that the inner region is always a region without any time-like circular orbits, and the outer region is always a region with unstable time-like circular orbits. For an object that has a stable light ring, the inner region corresponds to stable time-like circular orbits, and the outer region corresponds to a region without any time-like circular orbits. And also shown that with these results, we show that for our horizontal-less objects with a pair of light rings, the region between the light rings are always have a region with any time-like circular orbits, and the same for the black holes, but instead between the horizon and the light ring. About the efficiency, we analyze it for several spinning scalar boson stars and for a family of spinning vector boson stars. We saw that the absolute efficiency in the first case is equal in the co-rotating, counter-rotating orbits and can grow arbitrarily close to unity. For the standard efficiency, the co-rotating orbits always show larger efficiency than the co-rotating ones, and the presence of self-interactions tends to suppress very slightly a bit the efficiency. Basically, the standard efficiency for axionic boson stars is quite, slightly smaller when compared to the mini boson star case. For the spinning vector boson star, we saw again that the absolute efficiency is equal for both co-rotating, counter-rotating orbits, and we also saw that in this case we can have stable time-like circular orbits until the center of the star, and we saw that the efficiency doesn't grows monotonically and goes very close to 100%. For the standard efficiency, we saw that it only appears for counter-rotating orbits, since there's only, for some compact stars, they are the only solutions that develop disconnected regions of unstable time-like circular orbits, as well as light rings. So, and we saw that the efficiency, due to these disconnected regions of unstable light rings, unstable time-like circular orbit, the efficiency drops to very small values. Finally, we also saw the efficiency for 2 families of black holes. For Kerr black holes with synchronized axionic hair, we saw that there are 2 types of solutions. We have solutions that are Kerr-like in its structure. We have solutions that are non-Kerr-like, which happens when there are some new regions of unstable or no time-like circular orbits. We saw that in the co-rotating orbits, the efficiency can be much larger than the maximum efficiency for Kerr black holes, and it can grow very close to unity in the case of Kerr-like black holes. And for the counter-rotating orbits, we saw that efficiency is smaller compared to the co-rotating case, but can be higher than the maximal efficiency for Kerr black holes. And finally, and to end everything, we also studied efficiency for Einstein scalar Gauss-Bonnet black holes. Here, the analysis was much simpler because all solutions all have a structure which is very Kerr-like. We saw that in the co-rotating orbits for small dimensional spin, the efficiency is slightly larger than the Kerr black hole with the same dimensional spin. But if you consider fast spinning black holes, the opposite happens. Regarding the counter-rotating orbits, we saw that the efficiency is always larger than the Kerr with the same dimensional spin, but this difference decreases as we increase the dimensional spin. So thank you for your attention and thank you for having me.
So we thank you, Jorge, for the very nice talk, and I'll ask everybody to turn on their microphones and cameras eventually for a round of applause in recognition.
Thank you.